All right, 18, and we're going to talk about hash tables today, which is really just another implementation option for symbol tables. So if you recall, symbol tables are generally storing key value pairs or sometimes just a key in a table. And we said, or in some structure, so we can kind of go get them back out again. And we said that sometimes we want to get things out in order and sometimes we don't care about order. So hash tables, as we'll see here, is a way of really quickly pushing stuff into one of these storage structures where we really don't care about the order, but we can get stuff in and out pretty quickly. And it's really quite a different way of doing things. And it will really be one of the ways we're going to kind of dive in via homework 5. So reminders, we have Friday lab, symbol table, key. That's a pretty straightforward one. Most folks kind of realize that was a quick one. We got a relatively quick one today. We're going to explore one kind of a hashing function, and we'll talk about what a hashing function is today. But the DJB hash is a pretty good way of turning a word into a number. So if you had a word and I needed to turn it into a number, that let's say I could use to look up in a location in an array, the DJB hash would be actually one good way to do that. So you can kind of look that up. Those are the initials of the inventor that I think created it. And if you like number games and prime numbers and all that kind of stuff, you'll love hashing because hashing has a lot to do with that. If you're sort of curious about cryptography also, this is kind of a close cousin to that. So a lot of the stuff that we're going to talk about is just a little bit of math, but it kind of borrows a lot from hashing algorithms and related in a way, encryption of different kind of keys and things like that. So we'll start talking about homework 5 and kind of set it up for you. So after today, you can probably begin tackling it if you want. I think you'll have all the information you need. You can always, just kind of dive in via Canvas and get after it. But most of the stuff we're going to talk about today is what you need for hash tables. And again, that is going to be using this doubly linked list. And we'll introduce what this idea is of separate chaining. That's a particular way of doing a hash table. There's a couple different ways of doing hash tables. One of them is called separate chaining, and the other one is called open addressing. And we'll talk about both of those over the next two lectures. So this is where Quizlet definitions will help you a little bit. So as we get into some of the terminology, it's, kind of unfortunately part of this course is we gotta, somewhat memorize or be familiar with terms. So you might want to just check those things out from time to time. It's really just a different version of our Canvas quiz. It's ungraded. So repetition is your friend here. If you get time to just take a peek at those whenever you're available. So today we're going to talk again about symbol tables. And again, the idea is that we're putting a key value pair, usually a key and a value in some storage structure, very often in the cloud. And we could just put in the keys, so in that case, we'd call it a set. But we'll just pretend we're dealing with key value pairs. And we'll, the questions we want to always consider are, do we want them to be ordered so we can pull them out in a range? Do we want to have duplicate keys or no duplicate keys? These are all kinds of questions we need to be able to answer when we design our symbol tables. So we saw that last time, and we said we can do really kind of, unsophisticated things, a linked list, or a binary search array, a little bit better, but not fantastic, or a binary search tree, that's a lot better. So that would be an ideal implementation for an ordered symbol table. We're not going to really spend more time in that area of the world because we kind of did our binary search tree, but that was kind of what we talked about last time. And there are other ways to do those symbol tables for ordered kind of keys. Today, we're going to switch over into the unordered area. And one of the benefits of saying we don't care about pulling things out in an ordered way, ordered by key, is that we can gain a lot of speed. And hash tables are one way of actually doing that. So hash tables are a data structure for implementing unordered symbol tables. Okay. So we have an abstract data type that sits on top of the data structure. and it kind of will interface with our underlying hash table there. And it actually is faster than binary search tree. So what's crazy is it's faster than log base 2 of the number of keys that are in the tree. You might think, how is that possible? So we'll see how we do that today. And that'll give you a good introduction to homework 5. So a couple reviews real quick. So remember that, inserting, we kind of give the key and the value pair when we insert it. And when we delete, all we have to do is specify the key. So if it's like, hey, I want to delete my Facebook account or my Gmail account, I provide my Gmail, and that is the key, which then is magically associated with the value, and all that stuff can be deleted. Or if I provide the key and ask for the value, then of course what I get back is everything associated with that key, and it can do all sorts of other kind of nominal checks about that key as well. Okay, so that's the general abstract data type idea there. And we said that, we can kind of map that to these methods, and you'll see this in your homework, right? You're going to basically be implementing this in homework 5 over the top of a hash table instead of a binary search tree, okay? And we won't be doing all those rank and min and max because that's not going to be supported by our hash table because it's an unordered kind of implementation of the symbol table, okay? So these things really are more associated with ordered tables, in particular if we were doing that binary search tree implementation. So we touched on that stuff last time, okay? But we won't be seeing that in homework 5, just to be clear, okay? Okay, so let's talk about hash tables, unordered implementation of symbol tables. So unordered basically means if you think about things like URLs, and in particular, if you look at what Program IZ is doing, and many other web companies as well, they put on that kind of string of characters there at the end. And we've seen this many times. Every time you share a link on the online compiler, you get one of these links, and it's all the same except for the last couple characters over there. So this is providing a unique key for finding a specific value, and in this case the value is your main.cpp file or your whole kind of playground, but in this case really we're just kind of pulling up a main.cpp file. So that's the value component of this. So there's no order, there's no real value in saying, hey, I want to list out all of the possible URLs in order, sort the keys, right? That wouldn't really provide us anything that's really clear, unless maybe we were being really sneaky and trying to find out who just created URLs today. It's like if I created one and I was like, ooh, they're creating them in order, so I'll just go poke around at the next one and the next one. Well, people figured out a long time ago that, that would be a really bad idea if you were Program IZ. It's like you don't want to generate these URLs in any sequential order because it allows hackers to go find those things. So they're going to randomize that URL in some way that spans as broadly as possible every possible combination of those letters up to some agreed number of letters. So when you look at that, you might think, okay, well, couldn't they run out of those things, or wouldn't there be some collisions in there? So it turns out if you have 13 digits, which is what they have, and you have the potential for every digit to have 26 characters in upper and lower case, plus an additional 10 numeric digits, 0 through 9, that's 13 slots or 13 columns of data with a total of 52 symbols, okay? So that is 13 to the power of 52, and that's a huge number. So they're really never going to run out of these URLs, right? There's no practical point in time in which that's going to happen. And it also gives them lots of room to spread out. So if they have a really good hashing algorithm that kind of hands these things out in a uniform way, well, they'll be spread out, and it's going to be kind of hard for people to go find stuff. You could go poke around out there, but you're going to be poking around in a really, really big area trying to find all of these private URLs that are out there, okay? And, we never store anything secure there anyway. Really, it's just our, homework and practice problems. So it's not like, we really need to worry about that too much. But that is kind of one example of where our key is uniformly distributed across this very, very big space. And the number of collisions that we might have is probably pretty limited, pretty small. Okay. So just by virtue of the sheer scale of the possibilities there. So it's a pretty cool little system. And, it only really takes 13 unique characters. That doesn't take up a lot of space. Okay. So this is an example of where we really don't care about order. You could say that we've got a hash. So that sequence of 13 characters there is sort of a string hash that we use to kind of look up something internally. So we'll be doing something similar to that. Not exactly the same thing, but it kind of gives you a sense of how these things work out in the real world. So what we want to do though is we want to take something like our key and turn that into some kind of a numeric value so that we know where to store something. And so that next time someone comes back with the key, we can use the same equation or algorithm to go find where that thing is stored without doing any kind of a search. So what we need is a mathematical equation or a little mini function that will turn a word or a character or a number into an array location and ideally avoid collisions. And then we just got to decide, well, if we do have a collision, what are we going to do about that? So that's the big idea behind hash tables is we have this function that kind of is like a funnel. It gobbles up something, a key, and somehow turns that into some numeric value. Okay. So we could use hashing for all sorts of stuff, right? So we can use this for URLs. We can use it for kind of detecting spam. There's a lot of things that we can do. And it turns out that with the good equation and a well-tuned strategy, we can do this in constant time. In other words, we don't go searching through a million things in order to find where we put something. We look at the key, and the key gives us the trick to find exactly where we put it. And we really don't want anybody to be able to hack our hashing necessarily if it's in a public area. We want our hashing algorithm to be sort of sufficiently cryptic that people can't figure that out. Now, if it's just for our code internally for hash tables, well, we don't have to be so cryptic about it, but we do want it to actually spread out the usage of our real estate appropriately. So we'll talk about how hashing algorithms need to be kind of uniform in the way they behave. Okay. So on a large scale, one kind of hashing is sort of turning a large amount of data. Think of Bitcoin mining, right? A schedule of transactions in Bitcoin that you want to crunch down into maybe a 256-bit digest. So that 256 bits is, usually represented as hex characters on the screen somewhere, but it sort of represents a thumbprint for a particular chunk of data. Okay, so that is, I would consider that to be kind of one kind of hashing that most of us may be familiar with or have heard about. So SHA-256 is the latest state of the art, theoretically uncrackable encryption to come up with that digest. So it's very, very hard for people to figure out, how you reverse engineer that. And that's usually used for very, very secure kinds of things, including blockchains, right? Which is really what Bitcoin is all about. We're going to be doing something a little less sophisticated, which is coming up with our own equations to take something a little smaller, maybe on the scale of bytes, like a word or even just an integer, and how to crunch that down into another integer that maps to an array. Okay, so just to put it overly simply, we're going to have a word that might be a long word, and we need a way of smushing that down into a number that we can then use to look up a position in some, reasonably smaller array. Maybe you got 1,000 storage positions or 100,000. So the number we get out of there is going to be a 64-bit number and we probably won't even use the full range of that, right? Because a 64-bit number would be a pretty big array, right? That's kind of like 4 billion or something. So we're probably really just talking something in the hundreds of thousands of ranges, okay? So that's our basic hash table lookup, okay? But they are kind of close cousins, and you can kind of read a little bit about this SHA-256 if you're interested. There's some really interesting tech over there, but we're going to be looking at hash table algorithms, okay? So you can think about it converting files into little digests versus strings into integers for an array lookup, okay? And you can kind of read a little bit about how Bitcoin works if you're curious about that stuff. It's actually kind of a fun project to simulate Bitcoin, but we won't go into that in this class. But let's take a look at what we are going to do with our array. So a hash table is really, in its simplest form, just an array. Okay, so we say, hey, create an array of size 6, goes from 0 to 5, and let's come up with a way of mapping our keys into these positions. And very often these positions are referred to as buckets. So a bucket is called a bucket because sometimes two keys hash to the same location. So that's kind of like a little collision. And we all know you can't really put two things in one array location in a simple way. So we just want to notionally for the moment call that a bucket, and we'll come back later to figure out how we put two things in one bucket. But the hashing algorithm itself is going to give us a bucket location, which is really just an array location, and then we got to do something about that. So if we have a bunch of key value pairs, and we have a hashing function, right? We're going to run the key through the hashing function, crunch it down into an integer, and then store the key value pair somehow in that position or bucket, right? And so if we have a good hashing function and we're a little bit lucky, we're going to get pretty good distribution, but sooner or later, we're going to have a collision, and that's just part of reality. We can't really guarantee that we're going to have perfect hashing. We can probabilistically have pretty good hashing, but by tuning some things, but sooner or later, we're going to have a collision. So how we resolve that collision, we'll talk about over today's lecture and the next one. But the idea of hashing is kind of fundamental to both kinds of approaches that we're going to talk about here, okay? So collisions and hashing are kind of some key parts of that, okay? And also the idea of a hashing function being deterministic. Okay, you wouldn't want to like hash something one day and the next day it's in a different place, like randomly or accidentally or from some numerical round off that wasn't, deterministic. We need to know that, if you have something like the word banana, it's got to go to position 12 every time we run it through the hasher. Okay, because otherwise everything sort of gets broken. Okay? So that's another key thing. So phone books, we could do things like, we'll just hash based on the first letter of somebody's last name. So in that situation, we're just really taking a key that's one letter. So that's a very simple key, probably not a really great one, but it's basically saying, okay, anybody with an A is going to hash to the same bucket in their last name, right? Everybody with a B is going to hash to another bucket. So we're going to have huge numbers of collisions in that case. So you can kind of see we have 2 there in the C category. So, in that situation, it's probably not a very useful hashing strategy because our buckets are going to have just a pile of things all jumbled up in there, right? And our main hashing isn't really buying us that much, okay? But that would be one way we could go about doing that, okay? Another approach would say, and we'll have to figure out how to deal with that collision. Reverse phone book. Okay, let's just take a phone number, run it through a hashing algorithm, come up with a bucket location, which you can think of again as an array position, and then we store a number or store a person's information based on that hash code. Okay, so that gives us a really quick way potentially to actually pull that information up. Okay. Now, probably we're going to have a collision. It kind of depends on how big our table is. So if we make our table really, really, really big, we probably won't have a collision, but we may have a lot of empty spaces. So when we do hashing, we never really exactly fully fill up the table if depending on our collision resolution strategy, right? We may not want to have a full table. We want to may have some stuff open there, okay? And again, we'll talk about how we do that collision resolution stuff. But here again, we're not really interested in who's got the next phone number one number higher. Okay. So we really don't care about the order in this case. So another common thing, and we talked about this with our other implementation the other day, is just tracking frequencies. How many times does a particular word occur in some large body of text? So this is for sure, or has been, one of the UC San Diego computer science homework assignments. It's like, here is one of Shakespeare's largest sonnets. Create a histogram for every word that Shakespeare used in 10,000 pages of text or whatever it is. So a hashing approach would be really good, because every time you read a word, you run it through the hasher, you go to the location where you stored the frequency, and you add one to that location, and then you go get the next word, right? And so in theory, every word should hash deterministically to a little bucket where you can go increment the count. So really great way to actually do a histogram or a frequency analysis. Okay. So in that case, our value is the count, and we're just changing the value every time we encounter a new word. Okay. So we could use our hash table for that. And we'll do this kind of in our lab today. We'll do something pretty similar to this in our lab. Okay. Now, binary search trees, yeah, we could do that, right? So, but one thing that people do is, in addition to having one-way pointers, is they create a hash table. So if you have a node value of 10 and you want to know what is the pointer to your parent, right? You can store that in a actual hash table. Okay. So you could say, oh, 10's parent is going to be a pointer to 11. Now that'd be a little silly, because we could just put the pointer right inside of the node here, right? But we could also just hash the key value, and it could provide us some stored reference to a pointer that we can use really quickly to move up the tree. Okay. So that is definitely one of the things out there that people do talk about doing. So, and then we, got to have different strategies for representing when there is no pointer, right? For the root, we would not have a pointer going up there. So that would probably be a null pointer. Okay. Now, another kind of not exactly hash code, but this is an interesting one I think about. It's interesting to read some of this information. Everybody's probably used or heard about Shazam. Shazam is pretty cool. So Shazam, what they're essentially doing when you Shazam a song to figure out what it is, you're creating a set of keys essentially based on the frequencies of the music. And those keys are sent as a combined uh, file, if you will, a small file that then gets hashed into a location for the song. So it really is a combination of keys. And if multiple keys hash to the same song based on the frequency you're sampling, then Shazam will say, okay, I know what that song is. So in that sense, it really is kind of a very sophisticated or hybrid kind of hash table. Okay. So you might have the spectral fingerprint from the section of the song you listen to. The song might be occurring in a particular key range or with a particular tempo, and it's going to send that information to the servers, and the servers are going to look it up and try to figure out what song it is. Okay, so this is a pretty cool thing. Obviously, it's been out for a few years. But let's talk about my kind of closer to our assignments, how we convert some of these keys into array position. It's really pretty straightforward, right? So if I have a key value, let's just work in the integer domain for the moment. So if I have a key value of 2001 and I have a table with only 10 slots in it and I want to map that, the easiest thing we can do is just, use our modulo function. So k mod m is always going to give us a location in range of 0 to m-1. Okay, so that's a pretty solid way of crunching any integer value down into the range that maps us to our current table size. So m is our current table size here. Okay, and that's going to be very clearly deterministic, right? Now, it does not mean that we're not going to have collisions. Of course, we could very easily have collisions, okay? But that's a pretty simple function that we can use, okay? So we can map 70 in there and we can keep going. And the easiest way to determine if we have a key is just to hash it, get the bucket ID or the array ID, and then check to see if we've stored something at that location. So obviously arrays all have to have a value, so we'd have to come up with some kind of a way in this very simple example of knowing that that thing didn't have anything. So you could initialize it to a -1 or some impossible value for which you'll never get a key, that kind of thing. Okay. But that's probably about the simplest hashing function we could think of. Just key, where the key is an integer value k, and we run the modulo to get the value or get the bucket location and then store it. Okay. Does everybody see that okay? Now you probably, or maybe in the back of your mind, you're thinking, okay, that's great, but if I have to increase the size of the table, it kind of blows everything up. And that's true. If we somehow ran out of space and needed to double the size of our hash table, that modulo function will no longer be deterministic because it was based on m, and now m is maybe 2m, right? So there are problems when we run out of space in a fixed size array. We pretty much need to rehash all of the keys in order to kind of move them over to the updated hash table size. So there are some challenges if we don't really have any more sophisticated way of dealing with collisions. Okay, we'll come back to that. I want to point out another thing, and this is something you can do in any language, but it's most elegant, I think, in C++ and probably even Java, is that if our key is a letter, every letter, of course, is as an ASCII ID, and so C++ will automatically just convert that into an integer value. So if we're trying to hash an individual letter into a location, we just use the same modulo function, and C++ is going to automatically convert that into an integer if that's what we're trying to actually, modulo it with and store it into some integer position. Okay. So it's really, really easy to just map those letters into any kind of table size we want. Okay. So we can put our character in there, and it's going to be deterministic. So B, etc. Okay. And that is, in fact, very similar to very much what we'll do when we're dealing with ASCII characters. And if we want to know if we have a C in there already, we just check to see if there's anything been initialized, if there's anything changed from the initialization of the array. So maybe it's set to a null character or something, right? So if we can do it with that, right, we can kind of, handle a range of things, characters and integers, at least for now. So somebody gives us a key, we modulo it with the size of the table, and we just return the integer value. And that's our super, super, super simple hashing function, okay? And we'll assume that, key is some kind of a signed integer, okay? And m is probably an unsigned integer. We probably should use the proper C++ size underscore t here, but I just like to keep it simple for folks who are not deep in the C++ syntax. But essentially those are unsigned values, or that's an unsigned m value. Okay, and so it should be deterministic. It really should be deterministic, and so we should be able to use that over and over again. Okay. So let's expand this to, a little more realistic application. So first off, reminding you of what the idea of buckets are. Really, mostly buckets are one-to-one with the array position. So if I say bucket 0, probably meaning, array position 0. Okay? But mostly the bucket is a conceptual thing. And it's conceptual because if I have collisions at position 0, I got to somehow figure out how to put multiple things in that bucket. So that's kind of where the idea of bucket comes from. It's like, hey, maybe I've got multiple things somehow at array position 0. So, but otherwise, I feel like the bucket term sometimes is a little confusing. You can generally think of it as being one-to-one with the array. Okay? But it is pretty much standard. So if I was mapping fruit names, and for some reason peach and plum mapped to the 0, then conceptually they're stored in the same bucket somehow. And we're going to look at a solution for that pretty quick here. Okay. So let's see. So we have an array, right? So we could have a really simple array where all we could really store is the key, if it was an integer or a character. So that, only gets us so far. And we could separately, like we saw in the last lecture, have a corresponding array that stores some value. So if it's a letter for the key and a number for the value, like a frequency count, then we could just do that with two separate arrays. That's okay. It's pretty low tech, but it gets you relatively far. Okay. We could also design a class or a struct and consider storing those all in one array. So um, hopefully we kind of realize at this point in our coding that an array could hold integers or it could hold an instance of a class. Okay. So structs and classes are really pretty much the same thing. They just have different policies about, who can access which of their data members. But essentially, it's just an instance of a class. And so that could have the key value pair inside of it. So that's kind of like a node literally being stored exactly inside of the array, not via a pointer, but actually, we've scaled up the array to fit the whole instance of that class in there. So that would be another strategy that we could follow. And that's not bad. Or we could, go one step further and say, well, let's just store a pointer in the bucket position that points to the node. Okay, and this is getting to be a little closer to what we were doing with our binary search trees, right? We've got a node, and then we got a pointer, and we just store the pointer in the array. So our array is an array of pointers to nodes, and every bucket is the head of perhaps a linked list. Okay. In this case, I'm just sort of saying there's no linked list, it's just one thing. But if we had collisions, we could use our linked list as a way of managing those collisions. So I could say, oh, okay, yeah, my hash table is going to be an array of some number of bucket pointers, or really node pointers. And every time we hash something to a bucket, we're going to add it to the linked list for that bucket. Okay. And now we actually have a pretty viable solution. Okay. And we've kind of warmed up on the whole linked list thing via the max priority queue thing. So we kind of know the game. It's like, okay, well, I got to insert. I might have to go find something. I might have to delete something, all that good stuff. And for homework 5, this is exactly what we're going to do. We're going to do it with double pointers. So we have our next and previous pointers. I've kind of simplified the representation here. And the pointer right here, and I know this will cause a bit of confusion. It always does. It's okay. But this is just a single pointer pointing to the first node in that particular bucket. Okay. So it is a node pointer, but it's not a node. The node starts down here. And maybe there's more nodes that follow. Okay. And of course, the last node has a null next pointer at the end. So this is what we call separate chaining. The strategy that we use here that we're seeing is called separate chaining. And this is what we're going to use for homework 5. Okay. So that's our homework 5 approach using double linked lists. So we'll need to hash, find the bucket, and if we don't want to allow duplicate keys, we're going to need to search to figure out if there's one there already. Now, as you can see in this picture, we have duplicate keys. So if we're allowing duplicate keys, it's kind of pretty easy. You just insert it at the top, right? Like we saw with some of us with our lazy insertion in our max priority queue homework, okay? But if we don't want to allow duplicate keys, it's a little bit of a more involved process. Okay. And that's actually where we're going to go with homework 5. Okay. So over here, we kind of have to say, maybe I can't deal with collisions, right? Or if I do, I need a different kind of strategy for what I'm going to do. And we will come back to what we do here, but imagine the game of musical chairs. where you come into a classroom and someone says, hey, I need you to go sit in seat 0. And you say, okay, seat 0 is taken. And the teacher says, okay, well, just find the next nearest seat you can find. Okay. So that works for inserting. But if someone comes into the class and says, hey, where's Jeff? I thought he was in seat 0. The teacher is going to say, oh, well, yeah, should be in seat 0, but look for him pretty close to there. That's what we call open addressing. Okay, and that is another way of dealing with collisions. And we will come back to that one. But just so you know where you are in the universe, this is what we're going to do in homework 5. And this is what we call separate chaining. So I'll continue to sort of review both of these approaches, but they both require a hashing function to initially find the location or the chair that we want to sit in. And then the separate difference is really, do we play musical chairs or do we actually just build a linked list? Okay. So let me pause there and see if anybody has any questions. We're kind of the medium level on that before we dive deeper. Okay. All right. So let's talk about this idea of load factor, which is kind of universal to both of these trees. And it's just one of the things that we kind of need to know. It's really quite simple, but it's the idea of how full is my table, right? So the number of keys stored or the ratio of keys stored to the total buckets, okay? So this thing is 2% or 20% full, right? This thing is 50% full. So high level is just giving us a nice number that we can use to describe the utilization of our table, okay? Now, this down here, we've got 12 keys in 10 positions. So it's 120% full, which might seem like not a good idea, but that's essentially giving us an insight into the average length of the linked lists per bucket, right? Or the average number of items per bucket, okay? So the definition isn't going to change, depending on whether we're using open addressing or separate chaining, right? It's always going to be the same, okay? So we're going to say keys stored divided by total buckets, even if we're using separate chaining to actually link these things together, okay? So that's one thing we want to have a handle on, and we'll quiz you on that and give you, Quizlets so you can kind of keep track of that, okay? And very often I'll use the notation N over M. So if you think back to our sorting, N was always the how many things. So N is going to be how many keys, and M, as in mother, is going to be the size of the table, just for clarity, or how many buckets that we actually have, okay? So if you see us using equations, that's what those things are, but I'll remind you of that. So that's kind of the two paths that we could take for hash tables. Let's go back to our hash functions for a minute and just look at some code and, get ourselves into, we only have 3 practice problems today, okay? So we want to produce a bucket ID, right? And so we could, modulo the max buckets. We could do this thing called binning, and this is kind of pseudocode here, but basically we could group things in regions by sort of coming up with a fractional value and multiplying it times x. So assuming x is already in the range of 0 to 8, right? We could multiply it by the number of kind of groups we want to put this in divided by the max buckets. And what that really does is it sort of shovels stuff that's similar into bin 1, bin 2, and bin 3. So, if you think of an Amazon storage facility where people got to go fill orders and they got to go into the storage facility to, they want to bin things that people buy in batches, batteries and flashlights maybe, right? So this would be an analogy for a binning strategy, okay? But we could do, ASCII codes, or if we had a string, we could do something as simple as adding up all of the ASCII codes and then moduloing that by the bucket number. So we're not stuck with just characters and integers. We really could sort of take it up a notch and start applying an algorithm to a longer collection of these characters, ultimately coming up with an integer value for our buckets. Okay. So these are all different approaches, and we'll look at more of these for sort of coming up with the mapping. And the DJB hash today that you're going to go through is really simple for your lab, and it's actually pretty effective. So if you don't have something like the DJB hash or something a little more sophisticated than just straight summing, you're going to end up getting a lot of collisions with similar words. And we don't want that. We want similar words to be really widely distributed across our entire table in a relatively uniform and ideally random way. Right? So, but we're going to dive into this and look at least one of these ways to actually do this. So we'll start out with a really simple way, which is just add up all the ASCII codes in a loop and then modulo that by our table size. In this case, I'm demonstrating that as a 10, right? So if I give you an ABC, you loop through, add up all the ASCII codes, modulo the final sum by 10, and that should give you your final location. So, but if we kind of do it this simplistically, you'll see pretty quickly we actually run into some collisions. So, 4A's is going to end up pretty close to where the AA is. Now, granted, we got a very small table size here, so guarantee we're going to get a lot of collisions. But if you think about it, it's not really spreading stuff out very well. It's more kind of binning things together, okay? But we'll do it just to kind of get ourselves started and see how the collisions kind of map out. Okay. So we may need more buckets, right? Probably we need more buckets, a bigger table, but we may need a more uniform hashing algorithm, something better than just doing that, adding up. One of the things that is often done is running it through a quadratic equation, right? X squared plus 6x plus 9 modulo 10, right? So whatever sum that you get, if it was an integer or if you came up with an integer, run that thing through a quadratic equation. Essentially, it's going to spread that hash location out over a wider range, okay? So the idea is not to have a double A being really, really close to a triple A, okay? So there's our key, in this case, an integer, and that's going to be our hash location, okay? So here we're just doing it with integers. Still, you're going to get collisions, but ideally, they're coming from different values, wildly different values, okay? And we can do that string technique we were seeing on the previous page to come up with this particular integer, okay? And there's lots of equations that people use, and we'll go through a number of them over the next 2 lectures, right? So if you like them, the math part, polynomials are exactly the way to go because they give you pretty good distribution of your final answer. Okay? Now, some of the things that hash functions allow us to do, just before we move on, it's good to point out. So if I want to know if 2 people are the same on the internet, right? If I'm kind of mailing out junk mail, and I say, oh, I got 2 Jeff Yateses here, right? One of them, lives at this address and one lives at another address, but all the other data is the same, right? So if we, rather than comparing all of the aspects of both of these to see if they're identical, a quick way to tell if they're not identical is just to compare the hashing of their keys. So however that particular database stores them, if you just compare the hash of their respective keys, if they don't line up, then you're pretty sure that they're not the same person, right? It's a relatively basic way to do it, okay? But rather than, searching through everything, you can kind of do a quick hash, compare the hashes, and then go further if the hash actually matches on some key, okay? But if they don't match, we can kind of exclude that and move on, okay? So this is one of the ways that we use hashing to sort of speed up searching for data in our databases. But let's go ahead and implement our first hash. So we're going to be given a string in this case. We're going to try to do the summation and then the modulo and see if we can get a working program here. And we can set our string size to whatever we want. But remember that we want to loop from I equals 0 to less than the size of our string. So if S is our string, we're going to be adding up all those values, storing it in a sum, and then performing the modulo before we return that answer. Okay, so let's dig into this, real quick and see if we can code this one up without too many problems. We only got 3 of these today, so shouldn't take us too long. Okay, so let's just take a look at what we got. We've got our hash function on top and just the main program down on the bottom. So I'll make this a little bit bigger. Okay, so somebody gives us a string. Let's just kind of dive right in. So let's say for int I equals 0, while I is less than s dot size and I plus plus. Okay, and I need a sum integer up here. So I'll say int sum equals 0. Okay. All right, and I will say, I'll just do it all in one line, sum plus equals s square bracket of I. Okay, so that's our sum. Okay, and then I'm going to return that sum, but I want to modulo it by m. Okay, so that's my hash for any string. It's not very sophisticated, but it kind of gets us going. For your lab today, you're going to write something a little more sophisticated than that. Okay. And then here in main, we're not really storing things right now. We're just testing out our hash function. So we'll take a word, run it through the hash function, get an ID back, and then print that thing out. Okay. So let's just test a few of these. Okay. And so we get to pick our table size. So I'm going to just start with a relatively small table. So our buckets go from 0 to 9. And so I'll just say, A, it's going to map to 4, A, maps to 1, A. Okay, maps to 8. So we're doing pretty good so far. And to be true, honest, the table's pretty small. So it's only a matter of time until we get a collision. Apples, okay, it's back to 5. Oh my goodness, yeah, we're kind of lucky on this one. Yeah, okay, 0. Okay, surely we're going to get a collision. There we go. There's our first collision. So it's not terrible, but you would see in a real world situation, if you hashed, 100,000 words, you'd certainly get a lot of collisions with something like that. Okay. But that's our first step in sort of implementing this hash table, is get your hashing function working for some string key. Okay. And probably better to add it all up and then modulo at the very end, right? You could try to modulo it every time, but that's still not going to save you from needing to modulo at the end because you're probably going to overflow your array. Okay. All right. So that's step 1. Now, if we want to do a polynomial hash function, it's pretty straightforward, right? We just sort of do the same thing, but then run our sum through our polynomials. So x squared plus 6x plus 9 modulo m should get better distribution. So if you play around with that a little bit, with maybe a little larger table size, you should get a bit fewer collisions on that. Okay, you can kind of play around and see what the behavior is. Okay, it's not ideal because of this part right here. This is a pretty unsophisticated way. We're going to get a lot of bunching up of our hash tables just predominantly because of that, right? But we'll look at some ways to make that better. And the DJB hash actually does that. Okay. Let's see if we can kind of take it up a notch. So we're going to try to have a key array and a value array, and now start to implement a working hash table using one of those hash functions. Okay. So if we calculate a hash, we're going to try to figure out if that position is already in use. And if it's not, we're going to store the key and the value. Otherwise, we're just going to throw up our hands for the moment and say, sorry, I got a collision. Okay, so in this case, we're not going to do any collision management. We're just going to kind of see how long it takes us to actually kind of blow up our program. Okay, so that's our bucket right there that we're going to be filling up. And notice I've got an empty space here. So if I have, let's say, backslash 0 or ASCII ID 0 there, then we'll assume that there's no key stored yet, okay, because that's going to be our null character. So in this case, we'd say that our table is 9 buckets, or 9 buckets used or keys stored over the size of 10. So that's our load factor, which is pretty high load factor right now. Okay? It's our 90%. So here's our setup. We're going to collect a word, collect a value. We're going to have a certain size for our table. We're going to declare the size of the array. And we can do this in C++. It looks a little illegal, but we're going to collect M here, and then we're going to use it in a array of strings that we're going to create at that point right there. Okay. So we didn't have to do any dynamic allocation for that. We just sort of created the array after we asked the user how big we want it to be. And we'll do that for our values. And then we will kind of go through and initialize those things. So we'll give this the empty string, and we'll give this, actually in this case, since we're storing strings, we won't be storing the ASCII 0. We'll be actually storing the empty string, which has a size 0. So that'll be a little cleaner solution. Okay. So that's our initialization. Our buckets used will set to 0 so we can calculate a load factor. Okay. So we have our kind of input, allocation, and then initialization. Okay. And string of size 0 at some location means unused or no key stored yet. Okay. And we don't have to worry about that array because it's going to automatically support string data. And string data is kind of, like an accordion. It will automatically grow depending on the size that we want. So let's just do this practice. This is 2 of 3. So let's see if we can do this until we get a collision, and we'll kind of break out of the loop when we do that. And so see how close you can get sort of to a full table. And look at how uniformly your keys are distributed. Okay, so let's dive in here. So we've got our hashing function. This is written for you here. So it's going to be just a straight sum and a modulo. Not great. So, we might not get really good results. But if you want to switch up to the quadratic one, just call the hash2 function instead. So we've got a hash function and a hash2. So you can swap out your hash functions and try different things if you want in your code. Okay. But here's us kind of doing the setup, laying out our keys and values, initializing them, right? So now we're going to start. Collect a word from the user. Okay. Enter a value to go with that. That's our key and value pair. Hash the word into a bucket ID. Okay. And then we're going to say if keys bucket ID equals the empty string, then let's store it. So we'll say keys bucket ID equals my word, right? So we're putting my word in the keys array. Okay. And the value associated with that is going to be my value. So we'll say values at bucket ID equals value. And then importantly, we will increment the buckets used, okay? Because we need that all the time for our load factor. Now, let's go through and print this thing out. So we're going to go from I equals 0 to M, right? No question? Oh. You're forgetting the bracket and the values. Thank you so much. I appreciate that. Okay. So we're going to go from I equals 0 to M. And if the key value is blank, then we're just going to print out, bucket, B for bucket, I with nothing in the middle. Otherwise, we'll say B for bucket I with a key value pair. So this will be our keys of I and our values of I. Okay, pretty simple stuff here. Okay. And then otherwise, we got a collision, right? This means we ran into something and we're just going to give up, right, and break out of the loop. And our load factor is going to be buckets used over M. Okay, so we want to get used to that equation because it's going to come up a lot. And let's see if I got lucky. Okay, nope. Values bucket I. Oh, yeah. That's where I goofed up. Thank you. I got a little excited about fixing that thing. Where did I do that? It was, should know to look at the line numbers. There it is. About that, bucket ID. Okay, let's see if that's it. Okay. Bucket ID equals my value. right? My value. There we go. All right. All right. Okay. So let's give ourselves 10 buckets. Okay. Hash function, enter string value, Jeff. Okay. Enter value 1. Okay. So that went into bucket location number 1. So key value pair. All right. So let's see if we can get lucky. Bob is the keyword. Okay. And 2. Okay. So Bob just ended up over here. Okay. Sam. Oh, man. I mean the comma. All right. 3. Okay. Okay. Still going. Right. So we're not doing too badly. Bill. 4. Okay. All right. Rob. I'm just coming up with names. Sorry. 4 again. Okay. All right. Well, I'll let you guys do that. But basically, keep going until you collide and pop on out of there and just see how well that actually does, that algorithm does. It's actually doing better than I would have thought. Okay. But in the real world, we'll need to do, a lot more than that. Okay. But that's kind of our first working example of a basic sort of hash table there. Okay. Questions on structure? Okay. All right. So we're not dealing with the collision just yet. So we're going to see if we can actually do that part to round out our day, and then we'll kind of call it quits. So this was our just super, super basic, not even trying to deal with collisions. Okay. Just I guess, yeah, a bit of a side mention again on uniform hashing functions. So the study of like how uniform is a particular hashing function for some set of keys, right, or some likely set of keys, is a pretty significant study. So if you're hashing people's names, you might have a different hashing function if you're hashing license plates, okay, or if you're hashing phone numbers. So you got to kind of choose the function that is going to statistically spread out usage across the whole set of buckets uniformly. And that's going to depend on the kind of key you're actually using. How many characters? Is it a full sentence? Is it a name? Is it a phone number, a license plate, a Moodle number, whatever it happens to be? So the idea of a uniform hashing function isn't one you just research and choose. It depends on the key that you're actually using. Okay. So one way we think about it is ideally it means that there's an equal likelihood of hashing into any one of the bucket positions. So the chance that a particular bucket is going to get a key would ideally be equal to any of the other buckets that are out there. Okay. So random letters should fill up that thing, a bucket 0 through 9 pretty easily. That would be a perfectly uniform hash. If we're really, really lucky, we would fill that up. If it was not very uniform, things are going to bunch up a lot if we were choosing random letters and hashing them into there. Okay. So that's one way of kind of determining or visually seeing that your hash is not very uniform. Okay? But that's what we want. We want to keep that as our goal. Okay. Even though probably we won't ever actually achieve that. Okay. So if we don't have uniform hashing, we have lots of collisions, we have wasted space. So that's the downside, right? So finding things becomes more expensive because we're basically not using the mathematical technique of finding something right away. We're just sort of finding a bucket where a lot of stuff is all jumbled together. So the first most effective part of the hash table is the hashing function, and it does need to be tuned to a particular kind of key. Okay. So let's look at collision resolution for our two approaches. So we've talked briefly about separate chaining. That's what we're going to dive into now, and that's what we're going to do for homework 5. Open addressing we'll come back to as this musical chairs approach on Tuesday of next week. And we'll introduce this idea of probing. That's kind of like we'll find the next available seat any way you can, and we'll talk about that. Okay, but this is the one we're going to look at for homework 5. So let's dive into separate chaining. We could find where something should be inserted, right? So once we know the bucket that it needs to go into, we got to decide what our data structure is going to be. We could do separate chaining, like directly linked list, or we could have arrays of arrays, like literally a hash table inside of a bucket. So that would be something we could do, right? We could have arrays of structures like we talked about, arrays of pointers to something, and that's essentially where we're actually going to go. Typically, it's going to be a linked list. It could be a pointer to a binary search tree. So we could literally hash to a particular location and then combine the use of that hashing with a binary search tree per linked or per node location or per bucket location. So let's look at a couple of these real quick before we dive into the code. So if I was to use a linked list, right, I'm going to hash something to a location, right? If it's a null pointer at the array, I'm just going to plug the node directly into that null pointer. Okay, so it's crucial that we initialize our buckets with null pointers out of the gates. If I hit a collision, right, and I don't really care about duplicates, maybe I just sort of push it in at the head or I push it in at the tail. Kind of depends on what our policy is. Okay. There's a 70, 84. So we're hashing. And at some point, somebody says, hey, I want to update key 70. Okay. So we have to go find key 70 if we're not supporting duplicates. And that's going to require that we potentially search all the way to the end of our linked list. Okay. But if our load factor isn't too big, the average length of our linked list shouldn't be super long, right? So maybe it's not super deep. And so that is a really, really short search. That would be ideal. It's a little bit like, balancing a binary search tree. So we need to go find that key and then update that particular value in that particular node structure. Okay. And so this is pretty much what we're going to do in homework 5. Now, we could do something crazy in hybrid, which is just put a binary search tree at every one of these bucket pointers. But by that point, you might as well just implement a binary search tree. Okay, but there's probably some hybrid implementations out there that would actually do that. Okay? And then you kind of get the best of both worlds. Okay? But we're still putting pointers in our buckets. Okay, to our node pointers. This is kind of, so yeah, let's just talk about strategy here real quick. So we're going to compute the bucket ID, right? We get an index. We're going to check to see if that index is filled by checking to see whether the pointer is null. And if it is, then we'll insert the new item into that linked list, okay? And then we just got to decide whether we're going to support duplicates or not, okay? And if we aren't going to support duplicates, we got to go looking through the whole linked list to make sure there's no duplicate and then potentially update its value like we saw, okay? So in homework 5, we are not going to allow duplicates. So you will have to search that whole linked list to sort of update that value, okay? And ultimately, you may find that it's not there and you can just store it, at the end or at the beginning, up to you. So that's going to be our strategy. We'll do a little bit of that here today in the time that we have left, but most of the work you'll still have to do on your own. It won't be too different. Okay, so here is our kind of find key. Just to remind you, if I say, hey, do I have 100? I have to hash that to a bucket ID. Let's say it goes to 0. Then I have to traverse the linked list to find out that there is no 100. And then I have to decide where I want to add it. Do I want to add it at the end? Do I want to add it in sorted order? Do I want to add it at the beginning? So you'll have some flexibility in homework 5 on deciding how you want to do that. Okay. Now, if we were going to support duplicates, it's really easy. Then you could just insert it at the head, right? And that's not a problem at all. Okay. Deleting is, as you might expect, you got to find it, see if it's there, right? And if it is there, you're going to have to cut it out. So some of the linked list, double linked list stuff we talked about in the last lecture will be useful for this part of homework 5. So make sure you go back to lecture 17 on that when you're kind of looking for that, so you don't have any crashes there. Our node class is going to be pretty much what you would expect. double pointers of the next and previous. So we're pretty familiar with that. And we have our key value pair right there. And then we're just going to do this. So this is a little new to folks. So an array of M pointers, okay? So that is an array of pointers that are null or garbage. We don't know. We should ideally go through and initialize them to null one way or another, okay? So that's our hash table. And it is eventually going to have multiple head pointers to linked lists. So position 0 will have a linked list. Position 1 will have a linked list. Or it'll be null, right? But each position I is a pointer to a linked list, potentially, right? Unless it's null. So we'll be definitely doing that. And we'll just keep track of how many nodes are in each bucket. Now, this is not the same as keeping track of maybe a histogram, right? So the number of nodes in a bucket is the number of collisions in that bucket. But if I was counting frequencies of words in a Shakespearean play, that's going to be the value component of the node. Okay, so we want to not mix those two things up. This is kind of the collision count. I should probably call that collisions on bucket M would be a little bit clearer, or collisions of size M. So when we want to create a new node, we do our usual node star temp equals new node, key value pair, okay? And then I want to see if for example, and this is just snippets of code, if I wanted to check whether a particular location of the hash table was empty, I'd just say if hash table of I is null, then let's say plug in that node at the head of the linked list. So now hash table of I is the head of the linked list, okay? So if you were to delete that node, later on, you have to set that hash table I position back to null. And this is where a lot of crash bugs will happen in homework 5, okay? Okay, so remember, you gotta kind of take care of the head pointer as the I position in there, okay? So you can grab onto the head like that. You could say node star temp equals hash table of I, and now you've got a hold of the head pointer for I. It might be null, okay? Or it might be pointing to something, okay? And you can test whether it's pointing to something, and if it's not, then maybe you'll go through the list with a while loop, okay? So this count array is just helpful for us to kind of keep track of how many things are in each bucket, but it's not really critical. We don't always keep count of that, okay? But it'll provide some interesting results. So what we'd like to see in homework 5 is something like this: bucket 0, a nice bar, and then list of the key value pairs in there. And we're going to do a lot of, the testing unit tests for homework 5 is pretty comprehensive. So we'll be crunching out hundreds of buckets and thousands of words in there. So you won't have to write that code, but you'll if there's a bug in your code, it'll probably find it pretty good. Okay. So if you get a collision, then you should see that something collides, and then it should add it to the linked list, etc. And ideally, that's some indication of the order of your linked list. That'll help you debug it, okay? So if you're getting crashing when you're inserting and getting a collision, then it's probably good to be able to see clearly, what your linked list looks like before you crashed, okay? The other really good hint I'll give you, and I'll remind you of this, have a really small table size on homework 5. Cause a lot of collisions early on so your linked lists grow and you can test your code. If you have a really, really big table, you're not going to get a lot of collisions, and it's going to be a little harder to test your linked list logic. Okay, so you might want to test with smaller table sizes if you're doing your manual testing before you try the really big stuff. Okay. Most of the time on homework 5, when people get stuck, I say, okay, let's turn off the unit test and just create a table of size 1, right? And just try that, or a table of size 2, and then go from there. So keep that in mind. Okay, so here's something we're going to do for our last practice problem, and that'll get you right into the lab. It's not the full implementation of your homework 5. So we're kind of switching on you here to a simpler implementation. We're going to have our counts per bucket, just like we saw, but we're going to just have an array of keys to keep the keys. And we're just going to try to keep counts of frequencies, I think is what we're doing. So here is our, the equivalent of our hash table in homework 5 would be like this, but we're not going to be doing that. We're just going to be keeping the keys in an array. So sorry to pivot on you all of a sudden, but we're kind of moving away from our homework 5 implementation so we can get to our lab here at the end of the day. So this is a simpler implementation than that homework 5, okay? And so in homework 5, instead of initializing our keys to a blank string like we're going to do now, you'd probably be setting I location to a null pointer. Okay, so hopefully those things will help you kind of keep your balance. Okay, and our float on our load factor will ensure that we are not getting a truncated value. We want to get a floating point value for our load factor so we can kind of see with precision kind of how we're doing. Okay. So using a float buckets used is one way of ensuring that when you divide the buckets used by the M value that you get a floating point result. Many people in homework 5 get a 0 half of the time on their load factor rubric because they kind of don't do the proper math there. So just keep that in mind, okay? So here's our while loop in main. This is going to be for our practice. We're going to say, okay, ask for a word, hash it to a bucket location, create a node, and we're doing a histogram on this lab. So we're going to set this to a count of 1, okay? And then identify where we hashed it to, and then we're going to check to see whether anything's in the bucket already or not. Okay, if there's nothing in there, we're going to hook up the node and we're going to increment the number of things in that bucket. Okay, so we haven't had any collisions yet. Okay, but we have incremented our number of buckets used because this was a 0 count. Okay, so nothing was in that bucket so far. So that's half of the code. It's already written for you, so it's not going to be anything you got to absolutely memorize. And we'll come back to that. Well, the rest of this we'll do inside. So let's kind of finish implementation of this, and I think we should be able to get you into the lab on time here. Okay. So let's look for the to-dos or the question marks. So our standard node structure is there. We got a nice, this is a special folding algorithm. So you don't need to worry about this, but if you want to use this for some of your future work on hash tables, this is a really cool little algorithm. It actually folds the string in a clever way and, minimizes your number of collisions, okay? So, and ensures that we actually are getting a reasonable fold. And then we pass it through our modulo back over here in our hash function. Okay, so all that's written for you. There's another hash function like we saw before, but let's take a look inside of main. We're going to zero out or initialize our hash table and the counts per bucket. Okay, buckets used is 0, collect a word. We're going to create a new node with the key and value pair. So we just say temp node equals new, new node, my word, and the value is going to be 1 because we've encountered that word 1 time so far. So remember, we're making a histogram here. So we start out with a value of 1, okay? And then if the number of things in that bucket so far is 0, then all we got to do is just hook that node up as the head pointer, okay? Assign the new node to the bucket's node pointer. So it's the head pointer for that bucket ID, okay? And we'll increment the number of things in that bucket, okay? And then the total buckets used across the whole table. Okay, so we got 2 different kinds of things we're tracking here. Number of things in our bucket so far and total number of buckets used. Okay. Now, otherwise, the bucket was not empty. So if the hash table key, right, at the head, hash table bucket ID key, that's the head pointer, or if the key at the head is equal to the thing we're trying to insert, then we want to increment the node's value member. It's like, hey, somebody just put the same word in. Let's update the counter. So I'm going to say hash table square bracket bucket ID square bracket arrow value plus plus. Okay. I'm saying go to the node at the head because it matches the word that I just read and increment the frequency of the number of times we've seen that word. Okay. You kind of got to imagine we're at the head of a linked list. We found it at the very beginning. And so that's an easy one, right? And we'll say incrementing duplicate counts for my word. Okay. Otherwise, it's a collision and it needs to be added to the linked list. Okay. So now we're just going to do the lazy thing because we don't have a lot of time for this one today and insert at the head. So we're going to allow duplicates on this practice problem, but we will not allow duplicates in homework 5. But let's just do the simple thing. And we'll say point the temp node's next pointer at the bucket contents. Okay, so what does that mean? We'll say temp node arrow next is equal to hash table bucket ID. Okay, so if the bucket ID is the head pointer, we're pointing the new node's next pointer at the head node. Okay. And now we need to point the head of the bucket location to the new temp node. So now I'm going to say hash table bucket ID equals temp node. Okay. That's our classic push it in at the head. Connect the new node to what is in the head. Point the array's bucket ID location at the new head right there. Okay. And now we've pushed that in at the head. And it's a duplicate, right? So it's not really a great solution, but it'll work. Okay. And then we'll just go ahead and print the list. So we're really waving our hands at the full solution here. We're not really doing the full solution, but we should be able to see some of this working. Okay. On line number 113, let's see what I got wrong here. Okay. Try so hard. Hash table, bucket ID, increment the node's val. Is it val? Oh, I think it's val, not value. Okay. Should be more consistent about that. Okay. All right. Let's see if we can do this. All right. So integer size hash table 10. Okay. Where to insert? 1. Okay. So we're only inserting words here. So 1 just happens to hash to bucket number 7. Okay. So let me put in 1 again and see if my counter works. Okay. There we go. So I've updated the value of that particular node. Okay. Now let's see if I can get lucky and get a collision with the words ones. Okay. I got lucky. So ones got inserted at the head with a count of 1. Okay. So I should be able to hit ones again and get a count of 2, etc. Okay. So now we have a kind of a working, I mean, sort of working, right? If I do this 1 again, you'll see the problem pretty quickly, right? It's like, oh, we never went looking past the head. So we really didn't finish this full implementation, okay? But we're on our way to doing what we got to do in homework 5. So we just sort of pulled up a little bit short on that, okay? So you're welcome to kind of finish that out in your lab, but it's not a requirement for you today. We're just trying to get you familiar with the structure of this so homework 5 isn't too much for you, okay? So here's the code here for reference. I think that's pretty much what I implemented there, okay? And as you can see, it says this is flawed, right? Not sufficient for homework 5. We're going to have to traverse that linked list and make sure there's no duplicates in there, okay? Okay, so it's kind of a strange thing. Okay, and then homework 5. So basically, just search through. You're going to need a while loop to do that. You've done that before. And if you can't find it, we're going to return a false. Otherwise, we're going to turn true. Okay, so that's if we're just searching for that key. Okay. Separate chaining, deleting an item. Kind of make sure you break it down into cases like we have for our linked lists. Check at the head, check at the middle, check at the end. I would probably even do it, check at the head, check at the end, and save the middle for last, like we did in our last lecture. That code will work better that way. Okay, but you can kind of find your own way on that. Okay. And so homework 5 is all there. So there's a very comprehensive test me there that will auto grade. So you'll know what your grade is up to 90%. Now, if you decide that the double pointers is too hard for you, you can opt out and just use single pointers, and that'll just be a 10-point deduction. Okay. So if you're like staying up all night pulling your hair out, maybe just kind of focus on your single pointers. I think a lot of you will actually do pretty good. Now, if you do a really good job on your overall performance of inserting these things, then there'll be a 5% bonus on top of everything. So in other words, try to find the most efficient way that you can insert stuff into your linked list so that you can have really a high level performance. Okay. So I'll just kind of wave my hands at that for now, but we'll come back and see how we assess that later on. Okay. So your homework 5 symbol table is going to kind of look like this. It's going to have a hash table. It's going to have something called max buckets. It's going to have linked lists, right? Some of those locations are going to be null. Double link pointers are going to be in there. Buckets used and current size is going to be the same as n. Okay. So that's going to be what we have called n today. Okay. And then M is the same as max buckets. So that'll be our M value called max buckets in your homework 5. Okay. And all of this other stuff, the constructor, the destructor is all written for you. The methods are hash function. Okay, so that one is, oh, you must write that. So you get to write whatever hash function you want. You can use the DJB hash from the lab today if you like. You're going to need to write your find node in linked list. Test the heck out of that one before you move on to anything else. That's a really foundational one, okay? Because every other method is going to use that. Insert key, delete key, get value, contains key, and load factor, okay? And don't truncate your division on that, okay? So we got about a weekend, a couple days on that. So sorry we're a little late to getting to this. I just wanted to make sure that we dive into that. Okay, so next time we'll talk about that open addressing thing, which you do not have to code up, but it is important for our quiz questions and our final exam. So that'll be an important one. And our lab today is pretty quick. Just dive in and do this one hashing function. And the hashing function is for each letter is going to be whatever the hash was previously, starting with 55381 times 33 plus the ASCII ID of the letter. Pretty simple, but super effective. And it's interesting to read about a little bit or have a chat GPT conversation. Shouldn't take you more than about 10 minutes to knock that one out, but it is a cool little hashing function for strings. And you're welcome to use that in your homework 5 as well. Okay. And I think that should be just about it. So I'll leave the rest of that for you to consider. Thanks for staying a little late. I'll hang around and otherwise see you guys on Monday. Thanks very much. Have a good weekend.